Hi, this is Sesh. In this video tutorial, you will learn how to do a topological sort on a directed graph using depth first search. I'm assuming that you're familiar with the depth first search algorithm and implementation. If not, you may want to watch my videos on these and then come back here. Consider this graph. Imagine that the vertices represent tasks to be done in some project, and the edges represent the dependencies between them. So the edge A to B, for instance, says that task B cannot be started until task A is finished, because B depends on information or data gathered in task A. Now let's sequence the vertices in this graph in such a way that these dependencies are obeyed. There are two possible legit arrangements: A, B, C, D, E, or A, C, B, D, E. Notice that in both cases, A precedes B, but there is no requirement that A must come right before B. As long as A comes somewhere before B, it's fine. There are two possible sequences here because the positions of B and C can be interchanged, since there is no edge between them. But A must be the first vertex since both B and C depend on it. Both B and C must come before D since they both feed into D, and D must come before E. This sequencing is called topological sorting. The word sorting here refers to the arrangement of vertices in a specific order based on the interconnecting edges, not on any numeric values. So this is a non-numerical sort. A topological sequence or sort is also called a topological order. Sequencing the vertices in topological order boils down to assigning numbers to the vertices, from 0 to n-1, where n is the number of vertices. So in our example graph, we need to assign sequence numbers 0 through 4 to the vertices. 0 would be the first vertex in the sequence, 4 would be the last. So here are the numberings for the two possible topological sequences. See that if there is an edge from a vertex x to a vertex y, then the number for x is less than that for y, as required by the dependency. The sequence numbers are called topological numbers. Now take a look at this graph. There is a cycle in this graph because there's a pair of edges between A and B in opposite directions. On the one hand, B depends on A, but on the other, A depends on B. This is a chicken or egg situation. Neither can precede the other, which means this graph cannot be topologically sorted. If we assign 0 to A and 1 to B, then the edge A to B will have its dependency satisfied, but B to A won't. And similarly, if 0 is assigned to B and 1 to A. So topological sort can only be applied to directed graphs without cycles, or directed acyclic graphs, known as DAGs for short. What we're looking to do is to come up with an algorithm that can assign topological numbers to vertices. And as you'll see, either depth first search, i.e. DFS, or breadth first search, i.e. BFS, can be called on for help in our effort. Let's think of how DFS can help us with a sort. The first thing that comes to mind is that we deal out topological numbers as we visit the vertices, like this. Starting the DFS at A, we deal out 0 to it. Then let's say we head to B next, to which we deal out 1. Moving on to D, we assign 2 to it. But wait a minute. D has an edge coming into it from C, which means C should get a number smaller than D, but the only numbers left are 3 and 4, both greater than 2. This is not good. So we are in a bit of a sticky situation here. We can't deal numbers out in increasing values as we visit vertices. We need to think of a different approach. If you want to think about this for a bit, go ahead and pause the video and resume when you think you have ideas you want to check out against the actual. So as it happens, there is a clever trick to this. What you do is to assign a number to a vertex just when you're about to back up from it to the previous vertex in the DFS process. So in the example, you will follow the DFS process from A to B to D to E. Then, since there is no path out of E, the process will need to back up to D. And now is when you want to assign a number to E. We can't assign 0 because every other vertex will need to get a number less than E. In fact, E should get the biggest number, which is 4. Okay, I'm sure you figured out now that the numbers need to be assigned in reverse order, starting with 4, going down to 0. So E gets 4. Backing up to D, there's no other path out of it, so we assign it 3. Backing up to B, again with no other path out, we assign it 2. Then back to A. Now DFS heads to C, and out of C, since E has already been visited, there's no option but to back up to A, so C gets the number 1. At A, we are all out of paths to take, so we assign it 0, and the DFS process is all done. The resulting topological sequence is A, C, B, D, E. Of course, if at the beginning of the DFS process, after A, if we had chosen to head to C instead of B, we would have come up with the other sequence, A, B, C, D, E. Since after numbering E and D, C would have been numbered with 2, then B with 1. Let's work out topological sort on another directed acyclic graph. Again, there are several possible topological sequences that can be computed, depending on which edge we decide to take first out of any vertex with several outgoing edges. It doesn't matter which, we just need to find a topological sequence. So here's one, applying DFS starting at A. Alright, so we can do topological sorting by using DFS with a minor modification, that of labeling a vertex just before backing up to the previous vertex in the DFS process. Let's see how this plays out in the code. Here's a recursive DFS method from the DFS video, which is implemented in the graph class, and the supporting neighbor and vertex classes. What we need to do first is to find the place in the code where the vertex V, on which this method is doing DFS, is just about to back up. This will happen after it has finished recursive traversals from all its neighbors in the for loop. So here, right after the loop. We can assign the current topological number, say n, to vertex V using an array called topnum to hold the numbers for all vertices. After assigning n, we need to decrement it so that it is ready to be assigned to the next vertex. The array topnum as well as n must be parameters to the method. Let's also change the name of the method to DFS topsort. Since n becomes a local variable, any change to it can only be communicated to the calling method via a return value. And instead of first decrementing then returning, we may as well just return n-1 in one shot. One other thing we need to do is change the recursive call to send in topnum and n as parameters, and hold on to whatever n comes back after the recursive call has finished numbering all vertices it can reach. It may have struck you that the returning n is not necessarily just one less than the n we sent in. Let's walk through an example to clarify. At the end of the process, the resulting topnum array looks like this. The array entries are the topological numbers, and the array indexes are the vertex numbers. Vertices are numbered arbitrarily. It all depends on what order they are read in from the graph input file. In this example, D is numbered 0, C is numbered 1, etc. So how do we write out the topological sequence? We first need to write out the vertex whose topnum is 0, to locate which we need to search in the array. We find it's the last entry and the corresponding vertex is A. Next, we need to search for 1 and write out B, and so forth. Searching for each of the topnums gets computationally expensive. In the general worst case, we will end up spending order n squared time to write out the topological sequence. This will happen if the topological numbers appear in reverse order in the array, which in this case would be 4, 3, 2, 1, and 0. A much better solution is to invert the whole thing. That is, use top nums as array indices and the vertex numbers as array entries like this. Then writing out the topological sequence is a simple matter of scanning the array and writing out each vertex as we encounter it. This will only take order n or linear time. To make this happen in the code, we need to change this statement by flipping the positions of n and v to this, so that n is the index and v is the array entry. Starting the traversal at A was a lucky move because all vertices can be reached from A and numbered. But what if we start the traversal at, say, C instead? In this case, only C, D, and E would be reached. Would topological sorting still work correctly? If you recall the Dfs algorithm, when all vertices are not reached from a starting point, the algorithm simply restarts from an unvisited vertex. And it restarts as many times as needed to reach all vertices. Restarts are done by using a driver that calls the Recursive Dfs method once per new starting vertex. This driver is a public method that is called by an application. We modify the Dfs driver by setting up a topnum array, initializing n to the number of vertices minus 1, and appropriately changing the call to the Recursive Dfs topsort method. Finally, we return the computed topological sequence. Verify that when the Dfs starts at C, E, D, and C will still get topological numbers 4, 3, and 2. The restart at B will assign number 1 to B, and the second restart at A will assign it the number 0. So the topological numbers are exactly the same as before. If you start at B instead, and then restart at A, the only difference would be that B and C will trade numbers. B will get 2, and C will get 1. But as we saw at the beginning, this is also a valid topological sequence. Alright, that about sums it up for this tutorial. Hope you enjoyed it. See you later.